Okay, welcome again, everyone. We are finally there to that special day where we can finally accomplish what I told you we were setting out to do from the beginning, and that is this is how we learn how to find e to the tm for some matrix m. Now, I'm actually not going to calculate this fully for you yet. We're going to calculate versions of that, but we're actually going to go a bit more general because there's nothing that's telling us we can't go general. So we will actually be calculating f of m for many choices of f. So that's really where we're going, is calculating matrix functions as a whole. There's nothing necessarily special about the matrix exponential except for how it, of course, interacts with ODEs. But we have enough tools at our disposal to do this for any function, any analytic function. So we will. So that's where we're headed today, and I'm really looking forward to it. Okay, so let's go on a little journey and think about a diagonal matrix. I gave it its nice eigenvalues. And we can take powers of that diagonal matrix, and it's pretty straightforward to see that powers of that diagonal matrix are going to give me powers of their eigenvalues. Which immediately means that if I'm taking sums of powers of the diagonal matrix, even multiplied by coefficients, I'm going to end up with precisely the sums of the powers with coefficients of each of the eigenvalues independently. Now what this is saying is that, hey, it's really easy to define polynomials of diagonal matrices. And I don't think this is a surprise to anybody that it's easy to define polynomials of diagonal matrices, but that they're so beautifully defined just as taking polynomials of the diagonal entries is maybe a little bit surprising. It shouldn't take you too long to get there, but it's a little surprising. But in fact, there's nothing that's saying that we have to stop at polynomials here. We can definitely do the same thing with analytic functions. They're just kind of, limits of polynomials. And we immediately recover that an analytic function on a diagonal matrix is precisely the function applied to the diagonals of that matrix. Okay, but here's something cool to think about. Something really cool to think about. If we have diagonalization of the matrix M, then we can represent it by an invertible matrix, the diagonal matrix, and then that invertible matrix inverse. And if we square it, we see what happens on the inside. Right, the inside, if we put two of these matrices together, right on the inside, that x inverse and x will cancel each other. And in fact, m squared is exactly equal to x d squared x inverse. And so powers of diagonalizable matrices are almost as easy to calculate as powers of diagonal matrices. Right, we gain the exact same property. For a diagonalizable matrix, we can find all of its powers just by taking the powers of the diagonal. But also by factoring an x out to the left and x inverse out to the right and pulling coefficients inside, it turns out we could do the same thing with analytic functions on this diagonalizable matrix M. And we can just diagonalize M, take the analytic function of the diagonals, and then convert our way back in terms of x. And so that's really, really a useful idea. And so we have a theorem here. And it turns out there was nothing really special about f being analytic. So right now I'm going to make that f is simply a function which can be defined on the spectrum of M. Why do I say it has to be on the spectrum of M? This is because in calculating f of the diagonal matrix, we will be acting f on the eigenvalues. Right, so all of the eigenvalues will go inside of f, and so we really want f to be defined on all of those eigenvalues. But once I have a function which is defined on the eigenvalues, it's really easy for me to define the function on the matrix M just by computing it on the eigenvalues and converting away from the diagonal matrix. There's something, so we'll look at an example here This is the diagonalizable matrix we saw in the last section, right? 1, 2, 0, -1, and we can construct capital X from that, which diagonalizes m to -1 and 1. And so let's just grab a nice function that we know how to define on -1 and 1. Maybe we grab this e to the x plus cosine pi x. It's a perfectly well-defined function. We're going to find out that f on the function or on the matrix M is exactly f on the diagonal matrix, which we can compute literally as f on each diagonal entry. And we get f on the diagonal entries, right? E to the -1 cosine minus pi and e to the -1 cosine pi. This should be a minus, I suppose, but I've corrected it in the bottom line. So right here, this is exactly the function f of m. And, a lot of you might be asking the question, okay, why not just take the power series representation, a n m to the nth power, where equals f of m, for f of x, which is equal to this power series, right? If it's analytic, then it's equal to a power series. Why not exploit that to our advantage and just take this as the definition of f of m? It's perfectly valid, but not closed form, right? This would be an infinite series. And so if we ever wanted a computer to play with that for us, it would have a really, really hard time, right? If we wanted to know some very nice properties about this matrix, it would have a really hard time. No amount of me adding, partial sums of this power series are going to tell me that that's actually what the function's equal to, even though, theoretically, if I managed to take the limit, I would get there. But doing this diagonal argument is much more efficient to actually evaluate, because it's very easy to evaluate these arbitrary functions just at numbers. Okay, so there's this really cool theorem then called the spectral mapping theorem. Okay, super, super cool theorem. In this case, I've restricted it to diagonalizable matrices. And that says that a function defined on the spectrum, we can compute the spectrum of the matrix function, right? The matrix function is this weird thing that we've defined over here. The spectrum of the matrix function happens to be equal to the function of the spectrum of the original matrix. So in some case, we're like calculating the spectrum of a matrix with calculating the function of a matrix, which I think is a very cool theorem. And actually, this idea is how we make sense of chaos theory. Okay. And I probably shouldn't call it chaos theory. Chaos theory is this very pop math idea that none of the mathematicians are really going to tell you that they're working on chaos theory. However, some of their systems are chaotic. But this is how we make sense of it. Okay, this is really one of the strongest tools we have at our disposal to handle some really chaotic events in the real world. And we're going to get there in the third part of this course. We're going to get to just a couple examples of chaotic systems and how to make sense of them. And we'll definitely be using that theorem around then, although it'll look a little bit different. Okay, so what are we going to do if m is not diagonalizable? And I think all of you already have an idea of what we're going to do, because that's what we spent the entire last class period doing. And that's that we're going to take Jordan blocks. So this is why Jordan blocks are so important for us. We've got our Jordan block over here. If I take a function and I compute it on a Jordan block, it's not that hard to prove that the function of a Jordan block is precisely this upper triangular matrix, which I know looks really ugly, but when you start to think about what it actually is, you realize that it's not that ugly. So it looks horrendous, but then we'll talk about what it actually is. It remains, the image remains upper triangular, and if I just look at the rows here, let's take a minute to take a look at the rows. That row is just the first mi terms of the Taylor series of f at lambda I. Okay, so lambda I, recall, is like this eigenvalue, right? It's the eigenvalue where my Jordan block is kind of pseudo-diagonalized at. And the image of f on a Jordan block is just the first mi terms of the Taylor series, and actually those terms just shift to the right. Okay, so each time I jump down my block, I'm just shifting the Taylor series to the right. So at the end, I only have the first three terms, the first two term, and the first term. Okay, so it's actually much easier to construct than it looks like, and it comes from the Taylor series. All right, so that's how you can take a matrix function for a Jordan block, and then we're allowed to take the matrix function it's an analytic matrix function for any square matrix, because we know that any square matrix has a Jordan decomposition, or it has a Jordan form, right? It can be written as xj x inverse for some matrix x, and all of a sudden we know how to compute f, right? If we compute f on each of the Jordan blocks which end up in the Jordan decomposition, we compute f on each Jordan block from the Jordan decomposition, we can recover f of j, but actually that gives us f of any matrix. Now the only thing is that now all of a sudden these functions do have to be analytic, and they have to be analytic at every single lambda in the spectrum. So f must be analytic at each lambda in the spectrum. Okay, so if my matrix has 5 different eigenvalues in the spectrum, I need to choose a matrix which is actually analytic at each one of those. It needs to have a convergent Taylor series at each one of those. But once I do that, I just compute f at each element at each Jordan block by the above, right? This was f at each of those Jordan blocks. So you're going to replace that entire Jordan block with this entire piece that you've calculated. You replace that Jordan block with a new piece that you've calculated, and that Jordan block with yet another piece, because each one gets calculated at its own eigenvalue, right? But from that point, you actually have f of j, and once you have f of j, you can convert back to f of m. So this is the number one reason why Jordan blocks, or why Jordan decomposition is so important. This is number one reason why we care about the Jordan form. Okay, the whole reason I went through the entire last lecture is just for this theorem for all of us. But now we can do it for every single function. We know that these exist for any matrix, and then for basically any function, right? The very well-behaved analytic functions we can calculate on any matrix. And so hence we can calculate e to the tm, and we can do it exactly, right? We don't need to approximate this. We can actually do it exactly with the Jordan normal form. We don't need to approximate. No approximations with the Taylor series. So you don't have to rely on approximating, the exponential of the matrix with the Taylor series. You can truly calculate it exactly with this theorem. So let's see with our lovely matrix from the previous section. I know we all loved this one. So if we recall, we were able to find our generalized eigenvectors and then there was our one Jordan chain, there's the other Jordan chain. It gives us, that's one Jordan block, that's the other Jordan block. And of course I've written it there as well for this matrix M. And then suppose I want to compute the function on the same function I had before, right? E to the x cosine pi x. All I'm going to do now is calculate f of that Jordan block, this one, and then f of this Jordan block, which they get calculated, you'll recall, by computing the power series centered at those points, right? So we're going to compute the power series centered at those points. If I do that, it looks like the following, right? So this would be the first entry in the power series for f centered at x equals 1. It's just the function evaluated at 1. This is the first entry in the power series for f centered at x equals -1. And this is the same thing for x equals -1. So those are the first entries in f centered at the eigenvalues. And then here's the special case. Right here we recover, this is the second coefficient in power series for f at x equals -1. And that's because that's our eigenvalue. And so we calculate that by taking a derivative and evaluating it at -1. However, once we do that, then we can find we can actually calculate those, and it looks like this. So that's very standard for f of a Jordan form matrix, and then we convert all the way back to f of m using our x's, and we gain the following. And this matrix looks like it's somewhat silly, like why would we ever need this matrix? But there are definitely reasons why we would want to be able to evaluate this matrix perfectly for this specific function. And then it turns out we actually have a spectral mapping theorem here as well. So if we have any analytic function with a convergent power series expansion on the spectrum, right, just as we need, if we're able to calculate a matrix function, then we actually gain the spectral mapping theorem yet again. And this can be true for any matrix. They do not need to be diagonalizable, but our functions are now required to be analytic on the spectrum. So a part of this proof will be one of your exercises. Anyway, that's all I have. Thank you very much. I hope you enjoyed it.